Hello everybody, this is Mr. Bank and this is my two-dimensional motion projectile motion video test. So I decided to choose a sport. I really like sports, and I actually chose one that I'm terrible at. So I really enjoy golf, but I'm not that great at it. So you can see I'm in the park and I'm just chipping, and I'll let the video play, but I know this is two-dimensional motion because the golf ball moves to the right and it also moves up and down. So there's my data points for it. The data points are kind of hard to analyze with a dot diagram because there's motion in two dimensions, so I'll let the graph do that for me. But my origin and scale, I didn't take a meter stick out there or a ruler, so if I rewind to the beginning and zoom in, you'll actually see that my scale is the golf club itself. I went from the top of the handle where you hold it to the location right before the club head, which ended up being 31.5 centimeters, which converts to 0.315 meters. So up at the top, you can see the beginning of that, the 0.3 meters of the 0.315. The X and Y components, X should be horizontal, so I use the ground as a guide, and Y should be vertical, of course. It did move in two dimensions because the ball clearly moved to the right in the X component, and it also moved up and down in the Y component. Excuse me. So let's go to the graphs and analyze these. I'm going to begin with the X component first. So I'll get rid of the Y component information right away. Here's the position, and here's the velocity. So the top graph, my position versus time, looks like it's a linear fit. This is good because the slope of a position versus time graph is velocity. So if I highlight this right away, it looks like I'm getting a velocity of about 1.78 meters per second. It is positive because it was moving to the right in the video, and it's linear, so it looks fairly constant. I feel good about that because in theory, it should have an acceleration of 0 in the X component. However, this is the real world, and if I look at the bottom graph, it looks like my velocity is actually changing because velocity is plotted on the Y-axis. Not needed probably because mine looks nice, but if I decide to maybe zoom out a little bit, I'm going to pinch zoom. I can actually see that at the beginning I have a velocity of about 1.99 meters per second, and at the end it's pretty different from that, about 1.65 meters per second. So it's clearly changing. Doesn't really look like it's changing by that consistent of a rate. It's not extremely linear, but if I did want to figure out an approximate amount of how it's changing, it looks like negative 0.347. What the heck is this? Well, this is my acceleration. The slope of a velocity versus time graph is acceleration. Why would I get a negative acceleration then if it's supposed to be 0? Well, if I think about it, in theory, the acceleration should be 0, but that's only when air resistance is not present. This is the real world. In air resistance, when present, it slows things down. So if my golf ball is moving to the right in the positive X direction, the velocity should be becoming less positive, which means a negative acceleration. So if the acceleration and velocity are in opposite directions, it should be slowing down, which that's what air resistance does. So that actually kind of makes sense. All right. So let's go ahead now and analyze the Y component, of course. I'm going to get rid of the X, get rid of the slope, and do the Y component for the velocity. So if I look at the top graph, this is not a linear fit anymore, which kind of makes sense because I know there should be an acceleration in the Y, so I'm not going to analyze the top graph. I'm going to look at the bottom. Velocity versus time graph, I have a velocity of 1.845 meters per second at the beginning, positive, and at the end I have a velocity of -2. There's clearly a drastic change. The nice thing is, it looks like it's a constant change because it's a linear fit. So if it's changing by a constant amount, that means I have a uniform acceleration, and the slope of this graph tells me the acceleration in the Y component, which is -3.9 approximately meters per second each second. That means the velocity is changing by -3.9 meters per second every second in the Y component. This, though, is way off from what it should be in theory. In theory, on Earth, it should be -9.8 meters per second each second. But if I think about this again, that's only when there's no air. And clearly there's air in the real world. I wouldn't think it would differ by this amount though. However, I did not use a normal golf ball. I actually used a wiffle golf ball, a golf wiffy. which it is extremely light and has a very, very low density compared to a real golf ball. So what that means is that air actually influences it, affects it, way more than a golf ball. So if I recall a video with a feather and a penny falling, when there is air present, they fall at very different rates. So this actually kind of makes sense. It would have been nice to get an acceleration very close to negative 9.8 meters per second squared for confirmation, but I wasn't using a very dense object, so air affected it a whole lot and showed me a very different acceleration in the y component, almost like a feather falling through the air, which kind of makes sense. All right. Hope this helped. Hope I get an A on this. And most of all, I hope I get better at golf, because trust me, it is rough. All right, guys, good luck on your project.